Well, let me first thank the organizers of this colloquium. It's really an honor and a pleasure to be in such a place and with such a public, with many Abel laureates and friends. And it's really nice also to be together after the pandemic. It's maybe not the first, but for me the second conference with real people. And I think that just being together 2-3 days, it proves that it's so different to do mathematics, having a human-to-human interaction. So I'm very glad to be here. And I'm going to sit down because I'm writing. And actually, I'm not talking about something new. This is old work. So it dates of 2006. And it's in collaboration with János Körner, that some of you might know, who is a Hungarian mathematician who was in Bell Labs, and then he came to Rome at least 20 years ago, so I had the chance to meet him. And he's started in information theory, actually got the Shannon Prize for information theory in 2014. So I was working in the computer science department of Sapienza together with him, and he taught me a lot of things. So I will explain you this conjecture on colliding permutations. So first of all, let me just present this problem, which sounds like just a simple mathematical puzzle that you can do at the beach, just relaxing and play with it. And then I will give you the motivations for that. So it seems like a problem in enumerative combinatorics, but actually it's not really enumerative combinatorics. So for me, n is the set of first natural numbers. And I'll take the permutations on n. And I represent a permutation pi simply by the sequence of the successive images. So for me, pi will be pi 1 up to pi n. So it's a sequence without repetitions of the integers from 1 to n. And the basic definition for the problem to play with is that I say that two permutations, pi and sigma, in the same symmetric group, are colliding if and only if there exists an integer such that pi of I minus rho of I in absolute value is 1, which means that if you take these two sequences, there is at least one spot where the two permutations have a 1 difference. So I will difference of 1. So I will give you an example.
Why did you write them that way? To the left or to the right?
This is a permutation. All the digits, I'm just saying that there must be an integer from 1 to n such that the image of pi, the image of I via pi minus the image of I via rho, the difference is 1. Okay, I'll give you an example maybe of two colliding permutations. So I take pi equal 1, 2, 4, 3, 5, 6, and rho equal 5, 6, 1, 3, 2, 4. And you see that there is one place, where is it? Did I write it? Oh, those are actually, they are, let me see, they are not colliding. So if I take pi equal 1, 2, 4, 3, 5, 6, and 1, 5, 6, 3, 4, 2, they collide here. Because 5 minus 4 is 2. So that's a definition by 1, sorry. So they do collide. Actually, you can have more places where they collide. Here there is only one collision, but they might collide in more places. So the basic question we ask, we want to know when n is fixed, what is the...
Choose that word. Why do you choose that word?
Colliding, because it's like they clash in this. I mean, the difference. I'll tell you after. You want to know where they differ. Somehow, this difference, the difference of one, we call it collision.
And do 6 and 1 make a collision? Like in your example, you work in...
No, it's not. I will. Then there will be. There is another problem, which is cyclic collisions. Yeah, good. But it has a different flavor. I'll tell you why. So what you want to know, you look for the large. So n is fixed. Now you take a subset of permutations, and you want that pairwise, each pair of permutations are colliding, and you want to know what is the largest number of permutations in Sn such that they are all pairwise colliding. So you want to look for T of n, which is the maximum cardinality of C, C being a subset of Sn, such that for any pair pi rho, with pi different than rho, pi and rho collide. So the goal is the determination T of n, first of all, and eventually determine T of n asymptotically. So this is more, it's not really an enumerative combinatoric problem, but you can think of that as an extremal combinatoric problem. So here you have your enumerative. And here you have extremal combinatorics. So in enumerative combinatorics, what you look for, you want to calculate, yes?
I have a question. Is this one very special? Because you could ask the same question about being 0, right?
Yeah, yeah. In this case, the difference, it's another theorem that I will prove in the end. I will show it. That's, I proved it with Benoît Larose, and at the same time it was proven by Cameron and Koo. Peter Cameron in 2004, and it was a long-standing problem about intersecting permutations. So it started from there, and then we had variations. But I just want to show you how this problem, they fit more in information theory flavor in some sense. So like in enumerative combinatorics, you want to calculate the cardinality of certain families of combinatorial objects, and each object has to have the same constraint. So just to have a very easy example, you take X to be a binary sequence of length n, and you want to know, that's a very, very simple problem. You want to know the cardinality of all the sequences which are balanced. What do I mean by balanced? Like for if n is even, you want to have the number of zeros equal the number of ones in X. And we all know that that's a very easy number, which is and choose n over half, if n is even. Otherwise, you have the ceiling, the central binomial coefficient. So here, all the sequences of your set F have to have the same constraint. So it's an internal constraint. While in extremal combinatorics, what counts is more pairwise differences. So here, like in this problem, you can have a similar thing. So fix n again. And you want to know the maximum number, maximum cardinality of binary sequences such that for any two of them, so if you take x and y, two sequences, they differ. So being different means that there is sorry, actually I wanted to say maximum number of maximum cardinality of sequences such that there is a place where you have a 0, 1 and a place where you have a 1, 0, which is actually different. So you want to calculate the maximum number of such sequences having a 0, 1 and a 1, 0, which corresponds to the Sperner theorem you are calculating, which is the maximum cardinality of an antichain in the Boolean poset. Because having this type of differences, 0, 1 and 1, 0, means that these sequences, they correspond to two subsets such that they are not contained in each other. So that's the maximum number is given by Sperner theorem. So the maximum is achieved again in n. Choose floor of n half. But so the problem looks similar, but it's here you are calculating the cardinality of a subset where your sequences could be whatever. They don't have an internal constraint, but the constraint is pairwise. So 2 by 2, they have to have this constraint. Actually, there is an interesting definition given by Janos Körner. That's the triference of a sequence. So sequences are triferent if you take 3 of them and you have a place where you have, like in a spot, you have a sequence like 0, 0, 1 or 1, 0, 1 and so on. So that's the definition of triference. While two sequences are different if there is only one spot, well, there is a 0, 1 or a 1, 0. So this is the definition of the Sperner theorem is some kind of symmetric difference. And this has a valency in the extremal combinatorics in information theory, and I'll tell you more later. So in information theory, what counts is differences. So it could be pairwise differences, 3 by 3, 4 by 4, but that's the key information. So a similar problem was this one. Now you can fix n again. So that's another problem. And you want to know, so you have a certain alpha, which is an integer, smaller or equal to n. You have pairs of sequences. So you have two sequences, x and y. And you want to know how many differences there are of type 0, 1. I don't know, it could be like this. 0, 1. So here alpha would be 3. And you want to compute which is the maximum number of 0, 1 sequences of length n such that they have a difference in alpha places. And then if you call this quantity m n alpha, so that's the number of 0, 1 sequences such that they are pairwise different in alpha places, and then you want to fix alpha, and you put n to infinity, then you are interested in exponential rate of this number m and alpha. So you can then define r of alpha to be the limit of 1 over alpha logarithm of m alpha n. So that's the exponential rate of the m and alpha. So you have what is called asymptotic Gilbert-Warshamoff lower bound, which says that R alpha is at least 1 minus the binary entropy of alpha. So anyway, just this is not the problem. Yes? Yes.
So I have no idea of how you prove such things, but so this thing that you're defining, like the number of sequences that have a certain pattern, if I'm not mistaken, that defines like a regular language. And so that the languages can be recognized by a finite state automaton.
You mean in this context of a numerative combinatorics generally? No.
Yeah, like a regular language is a language that has a regular grammar,
Mm-hmm.
which is the simplest kind of language.
Like palindromic word or no?
And so such languages can be recognized by a finite state automaton, which is the simplest kind of automaton. And so, and they have a very nice representation with like states and cycles and so on. So that's your calculation of like of this number essentially kind of amount to counting how many ways there are in order to accept a given sequence. Maybe it's not very clear.
I'm not sure. Yeah, I'm not sure.
So you don't make a connection to regular languages.
No, not in this context. I just wanted to, for people who are not familiar with this extremal combinatorics problem with permutations of sequences, just to show the difference between the 2 points of views, the enumerative one and the extremal one, where you are interested in knowing a code in a sense. So a set of things that maximize, for instance, the cardinality when a parameter like the length is fixed, which is very different than questions in enumerative combinatorics. So the difference is pairwise count. Actually, recalling what Kathleen Westergombi was saying this morning, she said that in Budapest there was no combinatorics in '66. And I must say that in Italy still now there is almost no combinatorics. I mean, there is very little combinatorics. And when I came back from Canada, where I was doing algebraic combinatorics for my PhD, I knew this algebraic combinatorics, and then I went to a computer science department where there was János Körner, and he introduced me to extremal combinatorics and to the work of Lovas and all these fascinating other things in combinatorics. So I'm very, very grateful to him, and I'm still fighting in my department to have some combinatorics done. I remember in 2012 they wanted to cancel the only course in discrete math they had, so they have, and I had to fight very strongly. So I'm glad that, yes.
R of alpha, is it equal to 1 minus h of alpha? Maybe it looks like it's a problem of coding theory where the linear
It is.
code is the whole thing.
It's, yeah,
So
it.
it should be equal, right?
Sorry, what's the question?
I mean, the question is the way R of alpha, whether this is inequality, from 1 minus entropy, it equals the rate? I would think
It should be, it should be a lower bound. I don't know in which case it's equal.
Isn't there a simple formula for the number? It's just n minus alpha factorial times 2 to the alpha? There's actually agree outside the alpha spots, and then another factor where you put the points. What is the formula?
Sorry, so they have, so in at least, I think,
Double counting.
Oh, what?
You are double counting.
Right, but I mean, isn't there a simple, well, double counting? No. Okay.
just referring to the very first talk by
this one? The
very
diff-
first talk at this conference, which was about codes by Lubotsky.
Yes,
So
yes.
he had the notion of minimal distance of a linear code.
Mm-hmm.
Now,
Yeah, it's connected
minimal
to it.
distance, but the code is the whole vector space. Right.
Okay, so in that case, it should be the same.
No.
But this is not linear code.
Not necessarily.
It's not about linear codes. You don't assume that it's a linear subspace.
But you don't.
Not necessarily. You ask,
It's about any sequences, right? You just
there is
want
no
to have
structure.
Pairwise distance is at least, okay, this is at least alpha positions, right?
At least alpha, yeah.
But otherwise no restriction on the sequences. That's the way I understand.
Without, yeah, there is no structure on the things, yeah. Anyway, so I want to show you the state of the art of this Tn. So let's go to the problem that I was working on with János. So state of the art. So let's look for an upper bound, which is very simple. So it's easy to prove that T of n is at most, again, the central binomial coefficient. So the proof of it goes like that. So to each permutation pi in Sn, you can associate a 0-1 sequence 0 and just taking the parity pattern of the sequence. So you define P of m to be 1 if m is even and 0 if m is odd. And then you can just go to permutation pi 1 by n. And the parity pattern of pi is simply the 0-1 sequence P of pi 1, P pi of n. And the key easy observation is that, well, there are two observations. This P maps Sn into 0, 1, n. And if C is a subset of Sn such that every two permutations collide, then P is injective. So if two permutations are colliding, if you have the two sequences, and if there is a place where there is a difference of 1, then the parity pattern here will consist of two permutations which differ. So you will have a 0, 1, for instance, here. And it's injective, which means that if you take restrict P to C, then the cardinality of C is at most the number of balanced sequences, because if you have a permutation, the parity pattern of a permutations is a sequence which is balanced. The number of ones is n floor of n over half, and the number of zeros is the ceiling, or vice versa, I think. So this is at most n over floor n2. So that's a very simple observation. So what is more complicated to find is the lower bound. So let's just play a little bit with it. And let's see what happens for n equal 3. Then it's simple if you take the permutation pi 1, 2, 3, and you take the cyclic shift of that, then you have 1, 2, 3, 1, 2, 3, 1, 2, 3. If you take this subset of permutations of S3, you can see that they collide. So there is a collision between the first and the second, a collision between the second and the third, and a collision here, as for the first and third. So this is you know from the previous result that cardinality of C must be at most 3 over 2, which is 3. And in this case, the cardinality of C is 3. So T of 3, the maximum number is 3. Now, the little trick is to see that here, the pairwise collisions that you have in this very simple code of 3 permutations, you don't really need the 3. So if you take, instead of taking the 3, you take 1, 2 star, you take a wild card, and you do the cyclic shift of these 3, so you obtain 1, 2 star, 1, 2 star, and 1, 2 star. Then these 3 permutations, they still collide, because you have the collision here between the first and third, collision here, and collision here. So you don't really need a symbol 3. So this allows you to produce immediately, very easily, for n equal 4, a maximum code. So a subset of permutations of length 4, which has the maximum cardinality, which is 4, choose 2, 6. So basically what you do, you repeat this game, you take 2, 3, 4, 2, 3, 4, 2, 3, 4, and then you do the 1, 3, 4, 1, 3, 4, 1, 3, 4. This and this collide inside each of the 3. And then you simply add, here you add a 1, and here you add a 2. So in this way, you reach the collisions for all possible pairs. So here and here, and here and here. And they are 6 permutations. And that's the largest number. So 6 is 4, choose 2. This is your code. So the cardinality of C is 6, which is the maximum. Then we had some other constructions. We tried to do constructions for n equal 5, having some structures. Of course, you can program it on a computer, but we wanted to see if there is a way of producing maximum cardinality things. And what happens is that we discovered by finding some cute little constructions that you have actually, for these first numbers, exactly the sequence of the central binomial coefficients until 7. Then some other people later did some more calculations for larger numbers, and up to now what we know is that things work until 8 and 9, in the sense that here you have 8 choose 4 and 9 choose 4, the central binomial coefficients. And for 10, it should be, 252. We are not sure because Adriano Garcia from UCSD gave this to a student who calculated, he wrote to us that he has 251, well, which is still, very exciting. And then a few years later, a colleague of ours, Adolfo Piperno, told us that he found on his with some other program 252. And then I asked a few days ago if you could send it to me or how he performed it. And he said, oh, that's too bad. I cannot find it anymore because 2 of my personal computers broke. So I cannot find this code of permutations of S10. But, well, he told us that he found this number. So the conjecture I'm talking about, which is still open, that we formulated with János, is that, of course, T of n is n choose n over 2. So there is a second conjecture. If this is true, T should be 2. So the exponential growth of the central binomial coefficient is to the n. So if you go to the square root of n, T should be 2. So we still don't know any of these 2 conjecture. So I don't know if you might have some ideas after this talk, and we really would like to go on with this. So again, now I want to go to some lower bounds. Just to see how to play with these things. Let's first see a Fibonacci type construction. Which corresponds to union, this joint union of permutations. So it's simple to prove that T of n is at least T of n minus 1 plus T of n minus 2. That's easy because if you take a subset of Sn minus 1, which is a maximal code. What I mean by maximal code is a subset of permutations of maximal cardinality of pairwise colliding permutations. And I take D, a subset of Sn minus 2, again, maximal code in Sn minus 2. What you can do, simply here you have C with all your permutations, and here you have D. So this is n minus 2, and this is n minus 1. And then, of course, you add an n in the end, and then here you add n minus 1. So you obtain a subset of pairwise colliding permutations in Sn. And so C union D, Cn union D times n minus 1 is a subset of Sn of pairwise colliding. And so that proves that T of n is at least T of n minus 1 plus T of n minus 2. And then as a corollary,
How
Minus 2, yes, thank you. So the corollary is that T of n is at least Fn, the nth Fibonacci number. So that's a first lower bound. To get a better lower bound, you can have product constructions. So one can see that T of n plus m is at least T of n times T of m. And as a corollary, that gives the fact that the limit T, the limit when n tends to infinity of the square, the nth root of T of n exists. Okay. So the way you can do it, again, you take C, a maximal code of Sn, pairwise colliding permutations of cardinality T of n, and D analogously in Sm. Then what you can do for any fixed sequence X, I use this notation, X plus n, you simply add n to each digit, so this will be x1 plus n, xm plus n. So if you take d plus n to be x plus n, then again, all the elements in D plus n, they are pairwise colliding. So you can take pi in Sn, rho in Sm, and you can concatenate pi and rho plus n. This will be a permutation in Sm plus n. So basically what you do, you start from C, this is C, and to each sequence you glue a sequence in D plus n. So you obtain a code of length m plus n, and they will be pairwise colliding, because they will be either colliding here or colliding here, which gives the proposition. So thanks to this, thanks to the fact that we had the T of 7, sorry. I want to show you, yes, that T of 7 is 35. Then, for instance, T is at least the 7th root of 35, which is larger than this number, which is 1.66, which is better than Fibonacci. So that gives already a better lower bound. And in this way, later, in a paper with Gabor Shimony and Körner, and myself, we had in a different way, we proved that T is larger than the 4th root of 10, which is approximately 1.778. So that's, again, a better lower bound. So far, there is a paper of Kerner with 2 collaborators of last year, and they proved that T is at least 867. So that's the best known. Actually, sorry, they give this lower bound in terms of the logarithm in base 2. So in the logarithm base 2 is, I'm not sure now, I don't have this number written, but anyway, I think this is the best lower bound. I want to show you how these things, they have a flavor of capacity of a graph. So what's the link? So far it just looks a problem, a puzzle with no other meaning, but you can rephrase it as capacity of a graph, the permutation capacity of a graph. So the relation with the zero error capacity of G, it was defined by Shannon in the 56. So you have transmissions of symbols through a noisy channel. So here you have a channel. You have a sender. Well, I mean, you probably all know these things, so maybe I shouldn't define this. Are you all familiar with the Shannon capacity? Some yes, some says no. Okay, anyway, you have a sender and a receiver. So you can think of the channel as a phone line, and there is some noise. So the symbols that you are sending, they can be disturbed. So the sender has a V, a finite set of symbols. He speaks of the phone, and then the receiver can understand or not. So what happens, for instance, if you send a P and a B, sometimes they are confused. So certain symbols are easy to distinguish, like a T and a Q, but T and D are undistinguishable, and P and B are undistinguishable. So the model for the communication is the following. You take a graph. So you define a graph G, V of G, E of G. So V of G are the symbols to be transmitted. And two symbols, X and Y, form an edge if and only if X and Y are distinguishable. Well, sometimes I think Shannon took the complement of this graph, so he was taking the undistinguishability relation, but it amounts to have the same thing. So the goal is to use all the letters you have in such a way that you don't mix up the letters. So, for instance, if you take this graph, if the graph is C5, the 5 cycle, you have 5 letters, and whenever you have an edge, they are distinguishable. So you want to send letters only if they are distinguishable. So the best possible communication you can have is the click number of this graph. So the click number is the maximum cardinality of a complete subset of the graph. Because if you have a complete, all the symbols, they are pairwise distinguishable. But in this case, like for C5, omega of G is 2. So the idea of Shannon is that instead of using symbols, you can code symbols by words. Oh, I just have 5 minutes left, sorry. So you just wave if in 5 minutes I'm still talking, because then I'm... Anyway, so the basic idea is that instead of sending symbols, you send words. And so you have a concept of a product, a graph product, because you take Vg to the n, so words of length n. And now two words, x and y, sorry. Are distinguishable if there is at least one place where there are two different letters. So let's call, I don't know, let's call this A and B. So if there is at least an A and a B, for instance, here. So if there is a place of the word where you have two distinguishable symbols, you can say that they are graph different permutations because they differ in this place, in this model. So the model of this graph is the product graph, and then you look for omega of g of n, because now you can send words, so you are interested in this product graph product to the maximum number of distinguishable words. And this is generally, it's easy to prove that this is omega of g of n is larger than omega of g. So you get better info. So yes, yes, sorry. Thank you. To the end. So you are interested actually in this quantity, which is the limit of the square root, so the rate of transmission of this product graph, and this is what is the Shannon capacity of the graph G. So now there was a conjecture of Shannon saying that if you take, for instance, C5, you know that omega of G is 2, and he conjectured that the capacity of C5 is square root of 5, which is larger than 2. And actually it took many years before this was proven, and this was proved by Laszlo Lovász in a very, very nice paper, which is now also in the book, proofs from the book. So you actually gain in rate of transmissions if you use words rather than this. So now I just want to translate, if I have 2 more minutes, do I have? Okay. How these questions of colliding permutations fit into this thing. So now you want to look at this problem. So I want to have the capacity of infinite graphs. So you take G now to be a graph where V is the set of natural numbers, and E of G is infinite, can be infinite, but this graph has finite chromatic number. So again, you define the 2 permutations, pi and rho, in well, 2 words, any 2 words. So in Vn, so words in the alphabet V, they are G different if and only if, again, as before, if there is a place where you have x and y, and xy is in the graph. So if you take this particular graph, L, the linear graph, 1, 2, 3, 4, 5, and so on, you see that two words are G-different if there is a place where they differ by 1, any two words. And you can study the capacity of this graph. But in this particular case, the clique number of this graph is 2, and if you go to study the capacity of this graph is going to be again 2. So it's not very interesting. So the idea with Janusz was to look at the product graph, L of n, but to restrict the attention only to permutations. So you study the graph induced by permutations inside the product. And that's what you're interested in, and you look at omega of L of n of Sn. So this is the permutation capacity. The permutation capacity of L will be the limit over square root of omega of Ln to Sn. So generally, to study permutations, it has some applications, for instance, in flash memories, and there is a different flavor than just taking words. So so our quantity, T, before, is exactly this limit for the graph, for the linear graph. Then there are all kinds of variations that you can do on this problem. As I was mentioning before, you can have cyclic colliding permutations, so mod n, or maybe you can take other subsets rather than the permutations here. You can take unimodal sequences, or you can study. Recently, I was looking with a colleague of mine, Daniele Gewurz, another way of attacking this problem, which was look at stabilizer of the stabilizer into Sn of the first n half points, and then present a colliding set of permutations as a transversal of a stabilizer of this point. But we couldn't find an algorithmic way to see if we can produce a subset of colliding permutations of the right cardinality. So there are many different variations. I don't have time to explain that, but the problem is still open, and if you have some ideas of different kind, we would be very happy. Thank you.
Thank you.